Welcome to chapter 4.4, where we are talking about inverses of functions. So when we talk about inverse, we're talking about is the function one-to-one. So the inverse of a function is a rule that acts on the output. Your output is another way to say your y values of the function and produces the corresponding input. So therefore you look at your x. So what we're going to be doing is mapping your y to your x. Typically what we normally do is we put in an x and we get out a y. That's what we normally do. But for your inverse, it's the reverse. So we go kind of backwards. We go starting from your y and then mapping to your x. It says, so the inverse undoes or reverses what the function has done. Not all functions have inverses though, right? Because we were talking about how to figure out if a graph or an equation is a function, right? Not everything is going to be considered a function. Same idea here. Not all functions are going to have an inverse, but those that do have an inverse are considered one-to-one functions. So in order to verify if you have an inverse, right? So looking at these two, we want to know, are these inverses? In order to do so is that we are going to take your original f of x function and we are going to put it on the inside of the f inverse, or what we believe to be the inverse. So this just says put function, or I should say original function inside the inverse. And if what comes out is an x, that is an indicator that it is an inverse. And then what you do to one, you also do to the other. You therefore put the inverse on the inside of your then function. So you kind of swap it. So put the inverse inside the original. And if it then again comes out to be an x, it is a function. Now, this is how you say your inverse. This right here and this right here is your inverse function. I'm going to copy and paste that over here. Copy, paste. So those are your inverse. How we say this is you can say f inverse of x. We're not saying this is -1 or f to the -1 power, because inverse is not the same as 1 over f of x. That is not what an inverse is. Okay, so not the same. Whereas your original function is just f of x. Just say this is original. So if we wanted to verify that these two perhaps are inverses, let's call this one, instead of g of x, let's say that this is your inverse, f inverse of x. So to prove that it is an inverse, we're going to plug g of x in. I used this color before. I'm going to plug g of x in to my original function. So f of g of x, or my f inverse of x, is equal to f, and I'm going to plug in x to the 1/3 into my function, into my x. So we're going to leave space for where your x is, and we're going to cube it. So again, we're going to insert my x to the 1/3 inside, and then evaluate. Well, properties of exponents suggest that we are going to multiply 3 times this 1/3. So multiplying top to top, bottom to bottom, we get 3 over 3, which is equal to 1. So what comes out is just x to the first power. So far, this is a good way to start to prove. We do the same thing, but for the other one. This time, we're going to put in f on the inside of your function. X, so f inverse of x cubed. So we're going to put it on the inside here. So again, leaving space for where your x used to be to the 1/3, and then actually going ahead and placing the x to the third in, that being your original. And again, properties of exponents, this time we're doing 3 times 1/3, which is still 3/3 or 1. So again, you have x that came out. Therefore, these are both inverses of one another, meaning that these are going to be a 1-to-1 function. Or your original should say is 1-to-1. So recall that in order to be a function, our x values cannot repeat. Similarly, for an inverse, our y values this time cannot repeat. We also tested functions with the vertical line test, which means the opposite of that, or the reverse of that, is your horizontal line test. So with this in mind, we are looking for your y values that have been repeated. So take, for example, here, right? First off, can you figure out, is this a function? Well, the function test said draw a vertical line anywhere, and as long as it hits your graph only one, it's a function. But based on your vertical or horizontal line test now, is this function, this one in blue, is it going to have an inverse? Unfortunately, no, because your y value repeats twice. We can say this is x2 and y1, and this is x1, y1, and this could be whatever y1 is. You'll notice that we have repeated your y value now. So no, this does not have an inverse. Therefore, not 1-to-1. So I'm going to draw a series of graphs, and I would like you to determine if this will have an inverse, if it is 1-to-1. All right, pause the video, see if you can determine, is this going to have an inverse, therefore considered 1-to-1? Well, based on your horizontal line test, we just have to draw a horizontal line anywhere through your graph. It could be in the center, it could be at the top. And we said, as long as it only hits once, your y value doesn't repeat. So in this first one, you'll notice that it hits your function twice. So while yes, it's a function, right? It passes the vertical line test. This one does not get to have a natural inverse. So this is not 1-to-1. Your next one, though, even if you drew a horizontal line anywhere on your graph, it is not going to it is going to pass your vertical line test. Therefore, it is a 1-to-1 function. So it has an inverse. Whereas your next one, you can tell that it's going to hit your graph multiple times. Therefore, it is not an inverse. So not 1-to-1, does not have an inverse. The other one as well, we said does not have an inverse. So these ones don't have a natural inverse. If we wanted to manipulate your graph so that we cap off your domain. So let's say we said, okay, well, maybe we want this x squared graph, but my domain only goes from the values of 0 to infinity, right? Therefore, I only have to work with half of my graph, and therefore it could pass the our horizontal line test. So some of these you might have to manipulate the domain in order to find or create an inverse. So now let's take a look at what we would do if we are looking at some of your inverses and we're not given a graph. So it says one-to-one functions are important because they are precisely the functions that possess inverse functions according to the following definitions. Inverse switches their domain and ranges. So keyword being that they switch their domain and range, which in turn, we switch our x and y values when finding their inverse formula. Now that is super, super key because that just means we get to swap your x's and y's, therefore swapping your domain and range. So if you already know what the domain and range is of your original function, all you have to do is switch those two, and then you also have your domain and range of your second function. Excuse me. So for example 2, right, this one is expressed not so much in a chart, but if wanted to, I'll show you how to read your chart. But this just says, if we enter in a 1 into your function, you will get out a 5. So this being a coordinate 1, 5, and another being a coordinate 3, 7, and 8, -10. If we were trying to find the inverse of 5, keep in mind, this is your y value. This is your y value. Therefore, if we're trying to find the inverse of 5, we said that we're going to go in the reverse. We have your y now. We want to find your x. What does it map to your x? So if we have your y value, that matches the one over here, meaning your x value is going to be 1. So f inverse of 5 is equal to 1. By that logic, can you try out the next two? Well, f inverse of 7 says that, again, this is your y value. So when y is 7, you have right here, your x value that corresponds to it is going to be 3. Your f inverse of -10, that is your y value, will map to the 8 of your x value. So these are your y values here. And we are just working backwards to figure out what your x value is going to be. So typically on your graph, right, we plug in an x, so x is equal to 0 into your function, and then you find your corresponding y value. What we're doing is we're working backwards. We start out with your y, so in our case, y equals 2, and then we find what your x value is. So take, for example, over here, perhaps this is the coordinate 2, 3. And if I said, hey, can you find your inverse, right? You're going to start off with 3, going to 3, and then down to your x value, 2. So on your graph, if you're given a graph, you start with your y value, and then you find your x value. Now, if it's in a chart, so this is if you had a coordinate, but if we just quickly put this into a brief chart here, I'll just put this down here. Right here, x, y, right? We have 1 mapped to 5, 3 mapped to 7, 8 mapped to -10. Instead of going from x to your y, x to your y, x to your y, we're going in the reverse. we have your y value, we're going to find your x value. Y to x, y to x. So that makes a little bit more sense in the chart formation, then great, by all means, build a chart or use your coordinate. Now, when it comes to finding an inverse of your function, finding the equation, right? Let's say we don't have a graph at hand. Instead, we want to find an equation. For example, take linear. Linear is probably one of the easiest ones to work with to start. So step one, we're going to switch f of x to y. So step number one, we're switching f of x to y. Y is equal to 3x minus 2. Step number two, right? We talked about the above, switching your domains and ranges, meaning we switch our x's and y's. So that is step number two, is that we switch your x and y values. So you start off with a y, it's now an x. 3x is now turning into 3y minus 2. Then step three, we are solving for y. So get y alone. So the first thing that we might consider doing is adding 2 to the other side. X plus 2 is equal to 3y. Divide by 3. So y is equal to x plus 2 over 3. Now this looks like we're done here, but we want to recognize that this is the inverse of your original function. So step number 4 is to switch y to f inverse of x. F inverse of x is equal to x plus 2 over 3. This would be your final inverse equation. Now, these steps are going to be the exact same for each and every time. So if you want, and if that was all you needed, please start to pause the video and practice out B, C, and D. Now, when it comes to B, your cubic, right? We said, okay, well, first thing we do is we switch your f of x to y. Y is equal to x minus 1 cubed plus 2. Now switch your x's and y's. So x is equal to y minus 1 cubed plus 2. And number 3, we said start solving for y, get y alone. Now, keep in mind how we approached these problems back in chapter 1.8, where we said we don't want to cube things, or we don't want to cube root things too early, because it's not just going to cancel out this one, right? Instead, we have to get this term all alone because y is locked in there. So we need to subtract out your 2. X minus 2 is equal to y minus 1 cubed. And now that your cubed term is all alone, we can go ahead and cube root it. So we have the cubed root of x minus 2 is equal to y minus 1. Now, the reason why we don't need the plus or minus sign is that we're not actively solving for this. Instead, we're just creating the equation. So now that we got your x out of the cube, we're now going to, your y out of the cube, we're now going to add 1 to the other side. So y is equal to the cubed root of x minus 2 and then plus 1 on the outside. We're not adding 1 directly to negative 2 here because this 1 is found on the outside and this x minus 2 is together on the inside of the cubed root. Lastly, we are switching your y into f inverse. There is your equation. You could do this with something to the 4th, something squared, right? The possibilities are endless, but the pattern is still going to be the exact same. Same thing even if it was in a cube root to start or a square root to start, right? We're trying to isolate that term, getting everything over to the other side, right? All of the sessions or all of the lectures that we've had before is leading up to some of this stuff that we're doing right here and right now. So let's take a look at what would we do if we had a rational function. So the first few steps are still the exact same. Y is equal to x plus 5 over 2. X is equal to y plus 5 over 2. And now, again, we're trying to solve for y, but right now we have a fraction. So we could do one of two things. We could either break this up into two separate pieces, and now we have two fractions to work with, but at least your y is starting to get alone. Or if we wanted to, we can multiply out your denominator. So what you do to one side, you do to the other. That allows us to cancel on this side. And typically that's the easiest way to work with this, even if you had something in the denominator, x plus 2, right? For example, you're going to want to multiply x plus 2 out of there and throw it to the other side. So for us, we have 2x is equal to y plus 5. Subtract the 5. Now we have 2x minus 5 is equal to y. And the last thing, f inverse of x is equal to 2x minus 5. There you go. Now let's take a look at f of x is equal to x squared. Now they're telling us explicitly your domain here, right? They're telling us that x is greater than or equal to 0. Now, why do you think that is? Well, if we were to graph that really quickly into Desmos, I'm going to graph even a more basic one. Take that off, take that off, that off. Okay. Right now we have this function right here, right? This is y equals x squared. Does it pass the horizontal line test? No, right? Which means it doesn't have an inverse. That is unless we decide to change your domain. By changing your domain, we now can have an inverse. So trying to use your horizontal line test now, you can see that we do have the inverse. So when we go to approach this, right, we're talking about maybe perhaps restricting or changing your domain and range. So if we're trying to find the equation of your inverse, now that we know we could have one through this restriction, right? We're changing f of x to y, swap your x's and your y's, and now try to undo your square by square rooting your x. So f inverse of x is equal to the square root of x. But keep in mind though, right, your domain and your range. What's the domain of the original? Well, this is x is greater than or equal to 0, meaning we're going from 0 to infinity. Right? They've told us that to begin with. What's your range, therefore? Well, keep in mind, we have half of this parabola. So your range is your smallest y value to your highest. Well, your smallest y is at 0, 0, and we're going to launch upwards. So your range here is also from 0 to infinity. Now, when we go to swap your domain and your range, domain of the inverse, it's really now the range of your original. And the range of the inverse is the domain of your original. And let's see if that does hold true if we do graph an equation like this one. So I'm going to graph this one. And again, what is your domain and range? This being your inverse, this being y equals the square root of x. Well, your inverse here, right, is from 0 all the way to infinity on both of your x and your y values. Now, what's nice is if we are trying to graph them together at one time, they will start to intersect, right? Only at one value. And they're being reflected over the x is equal, or y is equal to x, y. So in the future, if you're ever trying to graph your inverse, you can find your y equals x line and then switch all of your x and y values. By switching your x and y values, we are essentially switching your domain and your range. Now, before we end our video, I would like to do a couple quick examples. So there should have been a worksheet handed off to you. Let's have you guys try 2, 3, 6, and 11. 3, 6, and 11. So pausing the video, seeing if you can try these out without us. So y equals the cubed root of x plus 2. X is equal to the cubed root of y plus 2. Subtracting 2 to the other side, we get y cubed, or the cubed root of y alone. To undo the cubed root, we're going to cube it all. So we have y is equal to x minus 2 cubed, or f inverse of x is equal to x minus 2 cubed. Now let's take a look at your domain here. So your domain of your function. Now think about what we talked about with your transformations. This graph used to look like this, and we've just transformed it up by 2. So went up, went up by 2. So it should look like this. Now, what is your domain of this graph? What should be all real numbers in your range should once more be all real numbers. And when we look at your inverse, right, this one, again, from your transformations, we should have gotten pretty familiar with the way that this should look like. So this looks like a graph that goes up and down rather quickly. It looks very similar to this one, which is a good indicator that they are inverses of each other. Except we have moved your graph over to the right by 2. So now it looks kind of like this. So what is your domain? This is all real numbers. This is because your range of your old expression is now the domain of your new expression. And your range here is also all reals based on your graph, but also because your domain of your old is the range of your new. Let's take a look at number 6. So y is equal to 3x over 5. X is equal to 3y over 5. Let's multiply by the reciprocal here. That way your 5s cancel, your 3s cancel. And what you do to one side, you do to the other. So y is equal to 5 over 3x. F inverse of x is equal to 5 over 3x. And again, your domain of your original, this is a graph, a line through the origin that just goes up 3 and over 5. So something that goes kind of like this. Your domain here, all reals. Your range is another all reals, which means if we wanted to graph this other one, it is still a line. This one is just going up a little bit faster and over 3. So something like this. Hopefully those match. So your domain here is all real numbers, again, because it is the same as your range from before. and your range of your or your new graph is the domain of your old one. Let's try a couple more. Let's try 11. Now, before we get started, let's take a look at your domain. Now, your domain here is going to be, kind of exclusive with some values. If you have anything in your denominator that has been canceled out, we have a vertical asymptote, which means we cannot be x being 2. Otherwise, if x is 2, then there's a 0 in your denominator. So that means your domain is going from negative infinity to 2, skipping 2, and going from 2 to infinity. We are not able to be 2, so we're open circle at 2, and then going on either extreme. So that's your domain here. And if we want, we can wait to grab your range if we'd like. And then we can graph these together and see what comes up. So this is already in y. So then we can do, switch your x's and y's here. Again, we want to get your variable out of your denominator, and we can't just multiply by y here and leave behind the 2 because your y minus 2 is acting as a team. So we need to multiply y minus 2 to both sides in order to get them to cancel. We talked about how to cancel out anything as far as a binomial goes and get it out of your denominator back in chapter 1.4. So you have x times y minus 2 is equal to y plus 4. Now there's, from here, we want to not go backwards and say y minus 2 or divide by here, because then we're back to where we started. Instead, we have to break open your parentheses here and say x times y, and then 2x is equal to y plus 4. And now we want to get your y's on one side. So getting your y values on one side, we can subtract y to the other side and add 2x to the other side. And then we can go ahead and see if we can factor out your y. The reason why you want to factor out your y is because you go from 2 y's into 1. So we get 2x plus 4, and then we can divide x minus 1 over here, x minus 1. That way this cancels on one side, and you're left with y, or f inverse, of x is equal to 2x plus 4 over x minus 1. So for us, right, your domain, your new domain here is what? For your domain here, we don't want to be 1. So your domain, we are just skipping the value 1 and going on either side. So we're going from negative infinity to 1, union 1 to infinity. Again, if you're having trouble with the writing of a domain or finding the restriction of the domain, please go and see that video about domain restrictions. So this just means that the domain here is going to be the range of your original. And the range of this one is really the domain of this one. And we don't know how to graph these rational functions quite yet, but to find your other restriction as far as your y values go, if the degree of your numerator and your denominator are the exact same, so 1 and 1, we take the leading coefficients of both. So this being 1 over 1 equals 1. This is where you're going to have a restriction on your y. This is a not vertical asymptote, but horizontal asymptote. So you have a horizontal asymptote at 1, which matches therefore your domain here. And you can see very clearly your domain has that restriction. And by that logic, if we were to take your degrees again, them being the exact same, we take the leading coefficient here of both. 2 over 1 is just 2, and this is the y restriction. This is the horizontal asymptote, which we then know this range to be true as well. Now, a good one to practice after that one is perhaps number 12, and I'll show all of your answers over here. So that's the first page and the second page. So I would pause the video or end this video and then go ahead and watch the inverse function extra practice worksheet.